Let me show you something here that you may not have realized before. If we were doing a Lewis dot formula for water, remember water is 2 hydrogens and 1 oxygen, and you share the electrons, and Lewis dot, or a Lewis dot formula gives you this formula for water. And this shows the electron pairs around that oxygen and the ones that are shared between oxygen and hydrogen. When students think about molecules like that, they often come to high school chemistry thinking that that's a static thing. That means it's sort of stable, okay? But it's not as stable as you might think. There's a lot of movement going on even in crystals and in molecules like this. So the bonds here, and this shared pair of electrons between this oxygen and this hydrogen, this is a bond. It's a sigma bond, a shared pair of electrons. There's a lot of movement going on there, okay? There's a lot of wiggling and twisting, okay? A whole lot of shaking going on. All right, that's an old song. All right? So every once in a while, when the conditions are just right, a hydrogen gets shaken off. Okay? Well, if you remember when we were doing the patterns on the periodic table, we said that the electronegativity of elements up here is higher than the ones down here. So, oxygen has a higher electronegativity than hydrogen does. And the definition of electronegativity is a relative measure of how hard one atom pulls on the electrons that it shares with another atom. Okay? So oxygen is pulling on these electrons more strenuously, with more force than the hydrogen is. So when this hydrogen gets shaken off, the oxygen holds on to the extra electron, the one that came with the hydrogen to start with. If you remember when we were putting together hydrogen and oxygen to make a water molecule, hydrogen came there with 1 electron. The hydrogen atom has 1 proton and 1 electron, at least most hydrogen atoms do. So hydrogen came to this bond with an electron, but it leaves without it. Does that make sense? When it gets shaken off in water. And there's a very small number of water molecules that always do this. So I don't care how pure the water is. You can spend a lot of money from a special chemical supplier and buy what's called ultra pure water. There will still be some water molecules that are broken apart like that. So there's no such thing as pure water, just so you know. Okay? So if this hydrogen gets shaken off, now remember, hydrogen atoms have a proton and an electron. That proton is positively charged, that electron is negatively charged. They balance each other out. So a hydrogen atom is neutrally charged. If the hydrogen leaves without that electron, what's really leaving? Just a proton. Okay? And what charge does a proton have? A positive charge. So if that happens then, what we have then is just a hydrogen ion, which is really just a proton. And it has a positive charge. Okay? Well, if that happens, then we also have something left over. So this is breaking off of there, and all this other stuff is still remaining. Okay? So you've got this hydrogen and these electrons. We're represented by the dots here. But now, remember, hydrogen brought an electron there. This molecule has an even number of protons and electrons, so this molecule has no charge. It's neutrally charged because the positive and negative particles balance each other out. But this now has lost a positive particle. What is new about this particle over this one? What's different? It has a negative charge. Good. Okay? So there's a negative charge on that particle. Now, this now is a polyatomic ion. It's a polyatomic ion because it's made of more than one atom. Polyatomic, right? And it has a charge. That's what an ion is. So a polyatomic ion is more than one atom covalently bonded together with a charge. Okay, a polyatomic ion is more than one atom covalently bonded together with a charge. more than one atom, covalently bonded together with a charge. Okay? And that is a polyatomic ion because it fits that definition. This polyatomic ion has a special name. We call it Fred. No, we don't call it Fred. We call it hydroxide. The students in my last class laughed at that joke. It hurt my feelings, guys. Okay. This is a monoatomic ion, which is really, in this case, also a proton. Okay? So this is a hydrogen ion, and that's a proton, and it's also a monoatomic ion because it's a single atom that is either has more protons than electrons or more electrons than protons. It's not an atom anymore because an atom has an equal number of protons and electrons. Okay? And this is a molecule, and we call it water. Okay? All right. Any questions about all that? Now, this process, this is called the autoionization of water. And it actually happens, like I said. All right. All right, so this hydrogen ion now is free. Well, it's not really free because it's got a charge. It doesn't want to be by itself. What does it really want? That's personifying an ion, which it doesn't have any real feelings. But, you understand what I'm saying. We're just trying to imagine what does it want to do. It wants what? Just one? Why did it join up here like this to share 2 electrons? It really wants 2, doesn't it? It came with 1, but it really wants 2. Okay? So here's our hydrogen ion. Well, I wrote it a while ago as a black lines. Okay? Black is beautiful, right? All right. And so it really wants 2 electrons. So it's floating around here in the water, and there's a bunch of water molecules here. Is there any place that hydrogen ion could get a pair of electrons? Huh? Yeah. You get a pair of electrons right there. Now, it's not going to pull those pair of electrons away, because remember, oxygen is very electronegative compared to hydrogen. But it could join up there. Oh no, we got something new. Let's see, this has a positive charge. The molecule was neutral. So what else do I need to draw over here? Yeah, it's got to have a positive charge because I've added an extra proton onto this water molecule. Protons are positive, right? Okay, so this has a positive charge. The whole thing. Okay, I can't believe I ate the whole thing. It's an old commercial. All right, it's an old Alka-Seltzer commercial. Well, this has a special name too, and it is a polyatomic ion. Because why? More than one atom, covalently bonded together with a charge. But its special name is hydronium. Hydronium. All right. Remember the molecule ammonia? What's the formula for the molecule ammonia? NH3. Good. So if we were to do that, or draw that formula out using the Lewis system, Lewis formulas, it would look like this. Hydrogen is covalently bonded, sharing 2 electrons with the nitrogen. And there's 3 of those hydrogens doing this, and there's a lone pair on this nitrogen. Okay? So this is normally a gas in its pure form, but we can dissolve it in water. Okay, so if I dissolve this ammonia in water, well, there's going to be some of those hydrogen ions lurking around there. Okay. And what does that hydrogen ion or that proton really want? 2 electrons. Well, could it get that from that ammonia? Hey, how about that? Join up right there, couldn't it? All right. And so what we get is this. And what else do I need here? A positive charge, because that ammonia had no charge when we started. We added an extra proton on there. The proton had a charge, so this thing has a charge. This is a polyatomic ion, because it's more than one atom covalently bonded together with a charge. And it also has a special name. And its special name is Jane. No, it's ammonium. Hydronium, ammonium. Huh? Oh, thank you. I appreciate that. Sounded like a little strained laugh, but thank you. Okay. All right. You got that? So this is your first introduction to polyatomic ions, and that's all we're going to do in this unit, just a little introduction of it. We've talked about monoatomic ions. We even did orbital notation, how we put those together using orbital notation, how we get the charge and things like that. In fact, in the last unit we did a lab in which we looked at how you get the charges by moving electrons around. But this kind of shows you a couple of really simple polyatomic ions in addition to our monoatomic ion, proton, hydrogen ion. Got all that? Everybody good?